Hello, you're welcome to today's class. In today's class, we're going to be looking at the internal forces in a beam. So the question says, determine the internal normal force, shear force, and bending moment at point C in the double overhang beam. Ignore the weight of the beam. So in order to solve this question, the first thing to do is to draw the free body diagram. Then you determine the reactions at the pin. So we have the pin A and we have the roller B. So you determine the reactions at those points. Then after that you cut the beam at that point C where you want to determine those three forces. So you solve the forces in that point C using either the left part of the cut or the right part of the cut, depending on the cut which have the simpler forces. So the first thing to do now, as we solve this question, is to draw the pin. Then is to draw the free body diagram. So I will draw the free body diagram, and I will label it as it is in the question. So here we have point A. Then around this part we have point C. Somewhere here we have point B, a little extended to the extreme. So on the beam we have a distributed load, and its apex is 3 kilonewtons per meters around point B. Around point B. So this is 3 kilonewtons per meters. So the distance between this extreme and point A is 1.5. The distance between point A and C is 1.5. Here we have 1.5, and here we have 1.5. So in order for you to convert this distributed load into a concentrated load, you have to look for the equivalent concentrated load. So let me tag this triangle as the triangle 1 and tag this triangle as triangle 2. So in triangle 1, we have to look for the concentrated load for this distributed load. In order to solve that, we use the area of a triangle. So for triangle 1, we have 1/2 times 3, which is the maximum load, maximum load, times the distance, which is 4.5. Here, when you solve it, you have 6.75 kilonewtons. And the point where it will add is determined for a triangle. The point where it will add, considering the apex, if you want to consider the apex, the point where it will add is given as 1/3 times the total length of the base, which is 4.5, and this will give you 1.5. So it will act on point 1.5 from the apex. So let us have that in mind. So for triangle 2, the maximum concentrated load given the triangle is derived as 1/2 times 3 times 1.5. This will give you 2.25 kilonewtons. And the point where this load will act on the triangle is 1/3 times 1.5. So from the apex, it will act at point 0.5 meters from the apex. So having gotten this, I will redraw the free body diagram again, and this time around we include those concentrated loads. So here we have, let me redraw it. Here we have the free body diagram, and I will call this my point A. I will call this my point C. I will call this my point B. Then I extend it a bit to get to the end. So the first thing is to include the reaction. So if you observe at this point A, we have a pin joint there. And for a pin joint, you have two reactions, which is the vertical reactions and the horizontal reaction. However, at point B, you have a roller joint there. For a roller joint, you have just one reaction, which is a normal reaction acting perpendicularly to the roller point. So let me represent that. So here we have at point A, we have this normal reaction, which I'll represent by AY, and we have this horizontal reaction, which I'll represent by AX. So I'm now including the forces. And remember, for this vertical force, for this this distributed force, we have one concentrated force, and it's acting on point 1.5, and this is 1.5, 1.5, 1.5, and we have 1.5. So it's acting at point 1.5 from the apex, and that is this point. Point 1.5 from the apex, because the apex is at point B. So 1.5 is this point, and you just put the force there, 6.75 is in kilonewtons. So the other reaction is at point B, where you have this normal reaction, and you call it BY. The last but not the least reaction is at point C, and I'll carefully draw it here, and that concentrated force is 2.25 kilonewtons, and it's acting from B. So let me erase this and write the distance, which is 0.5, while the distance here is 1. So we have succeeded in drawing the complete free body diagram. So what we just need to do is to go ahead and solve for the reactions. So in order to solve for the reaction, you find the sum of the moments are about point A, and we take the counterclockwise moment to be positive. So the sum of the moments is equivalent to taking the moment about point A, and in order to do that, we start from the first force right of A, which is 6.75, and if you want to take that moment clockwise is negative, so it becomes minus 6.75 times the distance 1.5. That's the first moment. The second moment is BY, and that is positive because it's going counterclockwise, plus BY bracket the distance from of BY from A is 3. The last force, the last moment, is also clockwise, so you have minus 2.25 times the total distance is 3.5 from the diagram. So this is equal to 0. So we say that the sum of the moment about a point in engineering statics is equal to 0. From this equation, you could solve for BY. And BY, if you solve this equation, you get 6 kilonewtons. You get 6 kilonewtons. The next thing we need to do, having gotten the reaction at BY, for us to get the reactions at A, is just to do the force balance. And the force balance is sum of the forces in the horizontal is equivalent to, we look at the free body diagram. We look at the free body diagram and we look at all the forces in the horizontal. So we have A as the first force, and that is the only force, and it says it's equal to 0. So automatically our horizontal force at point A is equal to 0. So we'll go ahead and look at the vertical force at point A, which is equal to AY. So we say upward force is positive, downward forces are negative. So you have AY minus 6.75, then plus BY minus 2.25. So we say that this is equal to 0. So from this equation, since we've gotten we've solved for BY, we'll just substitute the value into this equation and get our AY. AY is equal to 3 kilonewtons. So having solved for the reactions at the pin, the next thing we have to do is to repeat the free body diagram and then cut it at the internal force C, internal point C, and solve for the 3 forces there. So what I will do, I'll repeat the free body diagram here. Then I'll bring out all the forces. Let me bring out all the forces. This is point A. So in point A, we have this horizontal force as 0. We have the vertical force as 3 kilonewtons. Then at point C, we have point C here. Then we have point B. The force at point B is 6, and we have this force here as 2.25. So however, let us observe something from our question. You have the force at the apex as 3. Sorry, you have the force at the apex okay, you have the force at the apex as 3. So what we do, we have to look for the force that is acting on this point C when we cut C from this distributed load. We have to look at the forces at this point C. So we just solve a simple mathematics. If the force 3 kilonewton per meter is acting on 4.5, that is from the end to point B, what force X we act at point C, which is 3? A simple mathematics or a simple calculation we just be to cross multiply. When you cross multiply, you get the X is equal to 9 divided by 4.5, which is equal to 2. That means the force acting on the apex force acting on point C is 2. So what we are saying is that if I have to cut this diagram from point C to determine the 3 forces there, then I have to resolve this like this. So what I'm saying is that the apex force here is 2 kilonewtons per meters. So I got that from interpolation. So here we have 1.5. Sorry, let us not miss this. Let us not miss this. This force is reacting from this point. Thank you. So this is 1.5. So what we are trying to solve is to solve for the three forces at point C. We solve for the three forces at point C. And for us to solve for the three forces at point C, you either solve for the left hand side, or you solve from the right hand side. Like I said previously, I said you solve for the forces in that point using the simpler reactions. So I'll use the forces at the left hand side, but if another student chooses to use the force in the right hand side, our answers will be the same. So let us use the force in the left hand side. So this is what we do. So since we have a distributed force here, we have to look for a concentrated force using the new apex force, which is 2 kilonewtons per meters. We've solved this before, so we just have 1/2 times 2 times 3. So this will give us 3 kilonewtons. So that will be the concentrated force that is generated by this distributed force. So the point where that force we act on from the apex is gotten as 1/3 times 3, which is equal to 1. The 3 is the distance from this point to point C. That's 3. So the point where it will react is 1. So what I will do, I will just draw this again instead of drawing a fresh diagram. So I will just clean this force and put the force here from this point. So this force will be 2 and 3 kilonewtons, and this point to this point will be 1. Why this remaining point will be 0.5. So let me draw that cleanly. So I want to draw this point, the left hand side, cleanly. So I'll just repeat that again here. So I have this point C, I have this point A, I have this point, and this point is 1, 0.5, 1.5. And in this point A, I have two forces. This is 3, and this force is 0. This force is 3 kilonewtons. So this is what I have. So what we are looking for is these three forces: 1, 2, and 3. So I'll call this my NC, I'll call this my VC, I'll call this my MC prime. So those are the three forces. We have the normal force, the shear force, and the bending moment about point C. So what we just need to do is to use that bending moment formula again. We have sigma bending moment about point C. Bending moment about point C, we say is equivalent to, we take the bending moment about point C, and the first one we'll just use is this moment at C, which we have indicated as being counterclockwise, so it is positive. So you have M prime C. The next moment is from the left side of C. The next moment is 3, and that is going counterclockwise, so we say plus 3 bracket 1. That is the distance. Then the final moment is negative. Let's see. Yes, it's negative because it's going clockwise. You have minus 3 bracket 1 1.5. And we say the sum of the moments in engineering statics is equal to 0. From this, you could easily solve for your MC prime. So your MC prime is MC prime, which is the bending moment about point C, is equal to, the MC prime is equal to 1.5 kilonewton meters. That is how you get your MC prime. Remember, we said counterclockwise is positive. So since you've gotten your MC prime, for us to get the order reaction is just to find the sum of the reactions in the horizontal and the vertical respectively. So for some of the forces, some of the forces in the horizontal is equivalent to your AX plus NC, and we say it is equal to 0. Because your AS was solved as 0, therefore NC is equal to 0. The final one is the sum of the vertical force, F of Y, which is equivalent to, we have the AY. Remember that this is equal to AY, and this is equal to AS. Okay, so we have AY plus, minus 3 plus VC. VC is equal to 0. And recall that we solved AY before. AY was 3. So therefore, VC will be equal to 0. So that is what we've solved. So let us check the answers they gave. So remember, your NC is equal to 0 kilonewton, your VC is equal to 0 kilonewton, and your MC prime is equal to 1.5 kilonewton meters. Thank you.